Hello, this video is about Taylor series, which is approximating a function as a polynomial. One reason of approximating a function to a polynomial is that polynomials are easy to differentiate and integrate. So for example, let's say f of x can be approximated as a polynomial in the form of c0 plus c1 times x minus a times c2 times x minus a squared times c3 times x minus a cubed, and so on, where a is some real number. Then we can see that f of a is simply c0, since all these x terms, when a is inputted, goes to 0. Taking the derivative of this function, I get 0 plus 1 times c1, because the exponent of this term equals 1, times 2 times c2 times x minus a, times 3 times c3 times x minus a squared, and so on. So therefore, f prime of a equals to c1. Taking the second derivative of this function, f double prime of x is in the form of 2 times c2 plus 2 times 3 times c3 times x minus a, and so on. So therefore, f double prime of a is 2 times c2, which means c2 in this case equals f double prime of a divided by 2. f3 of x, which is the third derivative of f of x, looks like 1 times 2 times 3 times c3, and so on. So therefore, f3 of a is 3 factorial times c3, which means c3 equals to f3 of a divided by 3 factorial. Now, if I keep on doing this, I see that Cn, the nth coefficient, is in the form of Fn of a divided by n factorial. Therefore, f of x can be expressed as sigma of n equals 0 to infinity of f of n of a divided by n factorial times x minus a to the nth power. And this series is known as Taylor series. Now, a mathematician named Maclaurin had inputted a equals 0 inside the Taylor series, in which he claimed that f of x is equal to the sum of n equals 0 to infinity of fn of 0 divided by n factorial times to the nth power. And this is known as the Maclaurin series, in which usually the Taylor series that we use is in the form of Maclaurin series unless f of x is not defined in 0. So let's look at some example. Let's say f of x equals to e to the k to the x. Then f of 0 equals to 1, since e to the 0 equals to 1. F prime of x equals to k times e to the kx from chain rule. Therefore, f prime of 0 equals to k. F double prime of x equals to k squared times e to the kx. Therefore, f double prime of 0 equals to k squared. And if I keep on doing this, I see the pattern that fn of 0 equals to k to the nth power. Therefore, e to the kx equals to the sum of n equals 0 to infinity of k to the nth power divided by n factorial times x to the n. Or if I expand this, this is going to be 1 plus kx plus k squared over 2x squared times k cubed over 3 factorial times x cubed, and so on. Another example is f of x equals to sine of x, in which f of 0 equals to 0. F prime of x equals to cosine of x, and f prime of 0 equals to 1. F double prime of x equals to negative sine of x, and therefore f double prime of 0 equals 0. And f3 of x equals to negative cosine of x, in which f3 of 0 equals to negative 1. And if I keep on doing this, I see the pattern that among the odd coefficients, 1 and negative 1 alternate. Now, therefore, sine of x can be expressed as x minus x cubed over 3 factorial plus x fifth over 5 factorial minus x seventh over 7 factorial, and so on. And the another example is f of x equals to cosine of x, in which f of 0 equals to 1, and f prime of x equals to negative sine of x, and f prime of 0 equals to 0. f double prime of x equals to negative cosine of x, in which f double prime of 0 equals -1, and f3 of x equals to sine of x, in which f3 of 0 equals 0. And in this case, although it looks similar to sine of x, we see that the even coefficients are alternating between 1 and -1. And therefore, cosine of x can be expressed as 1 minus x squared over 2 factorial plus x fourth to the fourth factorial, and so on. Now, in physics, approximation using Taylor series is heavily used. So, for example, we've just shown that sine of x is equal to x minus x cubed over 3 factorial plus x fifth over 5 factorial minus x 7 to the 7 factorial, and so on. But when the magnitude of x is small, sine of x can be approximated as x, because x to the third power and x to the fifth power and so on, these terms are going to be all cancelled out. If we draw the graph of sine of x, then we see that near x equals 0, then f of x can be approximated as f of 0 times f prime of 0 times x, in which since f of 0 equals 0, since sine of 0 is 0, and f prime of 0, which equals cosine of 0 equals 1, this linear graph of approximation can be approximated as x. Therefore, sine of x can be approximated as x. Similarly, cosine of x equals 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial, and so on. And when x is small enough, all these x terms are negligible because x is so small. Therefore, cosine of x can be approximated as 1. And we can see this in the graph because cosine of x at near 0 is at the value of 0. And we see that since the slope at x equals 0 is 0, the value of cosine does not vary as much as long as x stays extremely small. And the second application is complex number. So for example, sine of x was in the form of 0 plus x plus 0 minus x cubed over 3 factorial plus 0 minus plus x to the fifth over 5 factorial, and so on. Cosine of x was equal to 0 at 1 plus 0 plus, this should be minus x squared over 2 factorial plus 0 plus x to the fourth power over 4 factorial plus 0, and so on. If I multiply the imaginary number I in sine of x, I get I times sine of x equal to 0 times ix plus 0 minus I times x cubed over 3 factorial plus 0 plus I times x fifth over 5 factorial, and so on. And if I add this, I get cosine x plus I sine x equals to 1 plus ix minus x squared over 2 factorial minus I cubed over 3 factorial plus x fourth to the 4 factorial plus I times x to the fifth over 5 factorial, and so on. But remember that e to the x was in the form of 1 plus kx plus k squared over 2 factorial x squared plus k cubed over 3 factorial x cubed, and so on. And in this case, k should be I. This should be e to the k to the x. Therefore, cosine of x plus I sine of x equals to e to the I times x from Taylor series. In addition to Taylor series, differential equation is also very useful in physics. And differential equation is an equation of the form of y prime of t equals to f of y. And there are two main methods of solving differential equation. And the first one is pure guessing. So for example, if y prime of t equals to constant omega times y of t, then this looks like y of t is in the form of e to the t. But remember that if y of t equals to e to the kt, then y prime of t from chain rule equals to k times e to the kt, which is k times y of t. So therefore, in this case, k equals to omega, and therefore y of t equals to e to the omega t. Additionally, we notice that we can multiply this solution by some constant a, and this solution will also fit into this differential equation. And the second method is called separation of variables. So for example, on the same differential equation, y prime of t equals to dy dt, and this equals to constant omega times y of t. If I separate the y on the left hand side and the other terms on the right hand side, then I get 1 over y dy equals to omega dt. And since all the y's are in the left hand side, I can integrate both the right hand side and the left hand side. And the bounds of integration for t is usually going to be 0 to t, and the bound of integration for y is going to be y of 0 to y of t. And this integral leads to natural log of y minus natural log of y of 0 equals to omega t. And this, from the characteristic of logs, equals to natural log of y divided by y of 0. And therefore, y over y of 0 equals to e to the omega t, and therefore y of t equals to y of 0 times e to the omega t. Now, we notice that the solution that I got from separation of variable matches the solution that I got from guesswork, in which, in conclusion, you can use either methods to get a solution of a differential equation. Now, let's look at another example. dy dt equals to negative ky squared times t. In this case, we see both y and t, but we can use the method of separation of variables to solve this equation. If I move the y squared term to the left hand side, I get 1 over y squared dy equals to negative kt dt. And I can integrate this from the bound of time from 0 to t and y of 0 to y of t. And from the integration, I get negative 1 over y squared from y of 0, y of t, equals to negative 1/2 kt squared from 0 to t. Canceling off the negative sign, I get 1 over, sorry, this should be 1 over y. 1 over y minus 1 over y of 0 equals to 1/2 kt squared. And therefore, 1 over y equals to 1/2 kt squared plus 1 over y of 0. And therefore, y of t is equal to 1/2 kt squared plus 1 over y of 0 inverse.